Okay, so electron velocity and electron position are complementary. The more we know about one, the less we know about the other. Electron energy is also complementary with position, meaning we can't know them both at the same time. And this makes sense because the kinetic energy is 1/2 mv squared. The kinetic energy depends on the velocity. So energy and velocity are related. They are both complementary to position. If we know the position of the electron, we can't know its energy. So the best we can do for if we want to specify the energy, the best we can do is we describe the electron's position in terms of an orbital, which is a probability distribution map. This just shows where the electron is likely to be formed, like that little drawing I drew about Andrew. The word orbital is very similar to the word orbit that's used in Bohr's model, but they are different. The orbit described the circle that the electron was traveling in. The orbital does not. It describes a region of space in which there is a probability of finding the electron. Many of the properties of atoms are related to the energies of the electrons. And so we generally focus on the energy of electrons rather than their position, because the actual position of the electron doesn't help us very much, doesn't help us to know that. It helps us to know what the energy of the electron is. So Schrödinger was one of the guys that worked on all of this quantum mechanics stuff. And he developed an equation that allows us to calculate the probability of finding an electron with a specific amount of energy at a particular location in the atom. Again, this is not saying that the electron is there, but we can calculate the probability that it is there. This is a complicated equation, and the math involved in all of this is way beyond the scope of this class. So we're just going to go for the big ideas behind it. So you can solve Schrödinger's equation. It has multiple variables and stuff in it. And the solutions produce wave functions. And those are given the symbol psi, which looks like a trident or something, a pitchfork. The wave function. That describes the wave-like nature of the electron. And if we plot psi squared, if we take that wave function, we square it, that represents an orbital, this region of probability where an electron is likely to be found. So from calculations, we can determine that the size, the shape, and the orientation in space of the orbital are determined by 3 integer terms in that wave function. So we've got 3 different integers, and when you plug these into the wave function, you come up with orbitals. So we need to know about these integers. They're called quantum numbers. So remember, one of the important things about the Bohr model of the atom is that the electron energies were quantized. It could be in this first orbit or the second orbit, but not in between. And that has to do with its energy, not with its position. So these are quantum numbers. The principal quantum number is n. The angular momentum quantum number is L. It's a lowercase l. The magnetic quantum number is m sub L. There's also a 4th one, that's the spin quantum number, and that's m sub s. And we're going to talk about each of these one at a time. So that principal quantum number. This determines the overall size and energy of an orbital. And these correspond to Bohr's energy levels. So if we think about the Bohr model, and we had the first orbit and the second orbit and the third orbit, or sometimes they're called shells. This principal quantum number n corresponds to those. N can be any integer greater than 1, greater than or equal to. So we can have 1, 2, 3, 4, as high as you want. The larger the n is, the higher the energy, and the larger the orbital size. And that corresponds with Bohr's model as well. For hydrogen, the energy of an electron with a quantum number n is equal to minus 2.18 times 10 to the minus 18th joules times 1 over n squared. So it's not too hard to calculate these energies for the hydrogen atom. Once we start getting into more complicated atoms, things get crazy. But we can actually calculate the energy. Now, when we calculate the energy of that electron, we're not knowing anything about its position. This is a negative number, and thus the energy is negative, because the electron's energy is lowered by its interaction with the nucleus. The electron is interacting with the nucleus, and that causes it to have a lower energy. Nature tends towards things with lower energy. If you have a boulder on the side of a hill and you give it a little push, is it going to roll up the hill to higher potential energy or roll down the hill to lower potential energy? It's going to roll down the hill. And so nature is all about getting things to a lower energy, more stable, lower. Okay? So that's why it's negative. Zero energy for the electron is when it's far, far away from the nucleus. So we're comparing it to that as zero. When it's in an atom, it's going to have a negative energy. As n gets larger, the energy gets larger, but also the energy difference between the orbitals is going to get smaller. And so here's a diagram. If we graph energy being up, increasing as we go up, for the principal quantum number n equals 1, an electron with that n is going to have an energy of minus 2.18 times 10 to the minus 18th joules. For n equals 2, it's going to be minus 5.45 times 10 to the minus 19th. So these numbers are getting less negative as we go up in n. The energy of the electron is increasing, which also means it's less stable. What I really want you to notice is that the difference between level 1 and level 2 is greater than the difference between 2 and 3. And 3 and 4 is smaller, and 4 and 5 would be smaller. And as you go up in n, the difference between the levels becomes smaller and smaller. So the next quantum number is the angular momentum number L. This is also an integer that determines the shape of the orbital. L can have an integer values from 0 to n minus 1. So whatever the principal quantum number is, subtract 1 from that, and you can have 0 up to that number. So let's just say that n was 3. Oh, that's not what I wanted. So if n equals 3, what are the possible values for L? It could be 2, it could be 1, and it could be 0. I don't care what order you write them in. It can be 0 up to n minus 1. So here's n is 3. That means the highest value of L is 3 minus 1, or 2. This determines the shape. And here we have L equals 0. These shapes are given letter designations. L equals 0 is S, L equals 1 is P, L equals 2 is D, L equals 3 is F. And is anyone curious why isn't it A, B, C, D? Well, yes, it does correspond with orbitals on the periodic table, but why did they call them SPDF? Those are good guesses. It actually has to do with the characteristics of the lines in the spectrum, the emission spectrum. And so S came from the word sharp, and P was from principal, and D means diffuse, and F is fundamental. So this was back before they were understanding what was really going on, and so that's where those letters came from. The letters are nice, because otherwise we end up with an awful lot of integers and it gets pretty confusing. So we use the letters, the letter designations. After F, they decided to be more sane about it, and they just went with the alphabet in order. So after F in the alphabet comes G, right? And then H and I. And so after that, it would just go in alphabetical order. But S, P, D, F. I should have some way to help you remember those, but I don't.
Will we ever really use them?
Some people don't fly. I don't know. Make up a sentence. SPDF. Some people don't fly. I don't know. We will be using SPDF. Then there's the magnetic quantum number. This specifies the orientation of orbitals, and hopefully when we come around to the end of this and put them all together, it'll be a little more clear. The direction in space that the orbital is aligned relative to the other orbitals. So whether it's an orbital that's up and down, or side to side, or sticking out front and back. This quantum number can have integer values from -L to +L, including 0. So if L equals 2, then M sub L can be from -L, which is -2, up to +2. So -2, -1, 0, +1, and +2. Each of these would correspond to a particular orbital. So there are 5 orbitals within this L equals 2. Then there's the spin quantum number. Electrons have, we describe it as spin. So if you want to imagine them spinning clockwise and spinning counterclockwise, that's fine, it won't mess you up. That's not really what they're doing, but if that works for you. It's just a fundamental property of an electron, and all electrons have the same amount of spin, but they are in opposite. It's a thing that is one way or the other. It's a little bit like the sex of people. You have female people and you have male people. Actually, let's make that dogs. You have female dogs and male dogs, okay? They're one or the other, right? So electrons can be either +1/2 or -1/2. It's the orientation of the spin. It's the same amount, but it's just in opposite directions.
So there is no 0.
There's no 0. So N is 1, 2, 3, 4, 5, 6, 7, 8, etc. L is 0 up to N minus 1. M sub L is -L to +L, including 0. And M sub S is +1/2 or -1/2. So each specific combination of N, L, and M sub L describes one orbital. So if we have N equals 1, the only option there is L equals 0. And the only option for M sub L is that it equals 0. This describes the 1s orbital. So if you studied like electron configurations in chemistry before, you may be familiar with 1s. Or even if you just remember, oh yeah, there was something about the 1s2, 2s2, 2p6, if that rings a bell at all. We call it a 1s orbital. The 1 is the principal quantum number, N equals 1. The S corresponds to L equals 0. M sub L, the number of different values of M sub L tell us how many S orbitals there are. There's only one. It has M sub L equals 0. So we say that orbitals with the same value of N are in the same principal level or the same principal shell. So N equals 1 is the first shell, and N equals 2, those orbitals are going to be a little bigger and a little higher in energy, because as n increases, the energy rises and the distance from the nucleus rises. If you have orbitals that have the same values of n and L, they're said to be in the same sublevel or subshell. So what if we had n equals 2? What are the possible values for L? 0 and 1. That corresponds to s orbitals and p orbitals. So for L equals 0, that doesn't even remotely look like a L, does it? I'll try that again. For L equals 0, what could M sub L be? It can only be 0. So that is the 2s orbital, the 2s sublevel, because N and L are the same. You're like, there's only one of them. Yeah, but it's the same for that one. So you're crazy. Yeah, I am. I'm talking to myself now. If L equals 1, what are the possible values for M sub L? -1, 0, and +1. So there are 3 2p orbitals. The different M sub L's tell us different orientations in space, and so we often designate those as X, Y, and Z along the axes of a three-dimensional coordinates. These 3 orbitals are in the same sublevel. They have the same values of N and L. So this is one sublevel and this is another sublevel. Together, these are in the same principal level. So we've got big groups and then it's dividing into smaller and smaller groups. Okay, so let's look at this diagram. For n equals 1, the only possibility for L is that it equals 0, and then ML has to be 0, and so we get a 1s orbital. For n equals 2, I did this one. We can have the 2s orbital for L equals 0. If L equals 1, now we have 3 different values for M sub L, and we end up with 3 different orbitals. Excuse me. So this big box is a principal level. This box here is a sublevel, and this is a sublevel. So there are 2 sublevels within this level. If we go to n equals 3, when L equals 0, we'll end up with 1s orbital. When L equals 1, we'll end up with 3p orbitals. When L equals 2, now M sub L can be -2, -1, 0, +1, and +2, and there's 5 orbitals. So this pink box is a sublevel. This pink box is a sublevel containing 3 orbitals. This pink box is a sublevel, and it's a little hard to see because it's kind of washed out, but this is a level, a principal energy level. Now, my husband thinks this analogy is really stupid, so I'll give you the option of hearing it or not. Do you want to hear how electron orbitals are like hotels? Sure, we'll bite on that one. Okay, so have you ever been to Las Vegas? They have some very interesting architecture in Las Vegas, right? There's one casino and resort that's shaped like a pyramid. Okay, so this you could imagine might be one of those creative architecture hotels in Vegas, except this was an inverted triangle kind of thing. Now, you couldn't build that in California because one earthquake would just knock it right over. But these are the floors. This is the first floor, and this is the second floor. And this is the third floor of the hotel. You get in the elevator, you press button number 3. Oh, I didn't mean to circle that. You press button number 3, you go to the third floor. And each sublevel in here is like a room. This room is closest to the elevator's over here. And here on the second floor there's a little more room, so there's this room, then that room. And as we go up, there are more and more rooms. Each level we add another room. The little orbitals here are like beds in the rooms. So when you go to the third floor, the first room you come to is the S room. S rooms have 1 double bed. And next is the P room. The P room has 3 double beds. Then you get to the D room. The D room has 5 double beds. On the 4th floor, there's S, P, D, and F, and the F room has 7 double beds. Now that's a weird hotel, isn't it? 1 room with 7 double beds in it. What's up with that? Yeah, it's weird. So each of these orbitals is like a bed. How many people can sleep in a bed reasonably? 2. Okay? And normally it would be a guy and a girl, right? Have you ever been on a trip, like when you were in, well, you are in college. I remember going on trips when I was in college, well, actually in graduate school. And we'd go to these conferences, and our advisor would get 2 rooms, 1 for the girls and 1 for the guys. And, you know, here there's 4 guys in a room. There's 2 double queen beds, whatever. Are 2 guys going to share a bed? No. 2 of them are going to sleep on the floor, right? They'll maybe switch off who gets the bed, or fight over it or wrestle for it or something. So here we can have 2 people in this room occupying the 1 bed, but it has to be a guy and a girl. That's the spin of the electron. 1 spins up, 1 spins down. Okay? So over here, you could have 5 electrons. If you had 5 electrons occupying this room, they would each take their own bed. Right? This reminds me of riding the bus when I was in college. You get on a bus by yourself, and you don't know anybody else on the bus. And there's some empty seats, and there's some seats with one person sitting in them. Are you going to go sit by a perfect stranger? No, you're going to take your own seat, aren't you? Because that's the socially acceptable thing to do. And who wants to sit by a stranger? I mean, you don't know till you sit down next to them whether they smell or not, right? So you'd rather just sit by yourself. So we'll find that the electrons, as they fill in these beds, these orbitals, they're going to first fill them individually, and they're only going to double up if they have to. Okay? So does that help at all? A little bit? The kind of the organizational structure is sort of similar there. There's a pattern to it. It's just strange is all. So the number of sublevels, those were the rooms, in a given level, the floor, is equal to n. So if n equals 3, you have 3 sublevels. If n equals 5, you have 5 sublevels. The 5th floor in the hotel is going to have 5 rooms. The number of orbitals within a sublevel is 2 times L plus 1. I go, that's helpful. And the number of orbitals in a given level is n squared. I don't use those relationships very much, but there they are. Use them if they're helpful to you. So, list the quantum numbers associated with all of the 5D orbitals. How many 5D orbitals exist? Okay, so I think the best thing here is just to think about it. So 5 tells us which quantum number? Principal, n. So n equals 5. So what does D tell us? It tells us what L is. L goes from 0 up to 1 before n. So for n equals 5, L can be 0, 1, 2, 3, or 4. What's D? It's third. S, P, D, F. It's the third one. 0, 1, 2. It's actually number 2. It's L equals 2. It's the third one in the list. How's that for confusing? So L equals 2. Now, if L equals 2, what are the possible values for M sub L? Minus 2 up to plus 2. Integers. So minus 2, minus 1, 0, plus 1, plus 2. So how many 5D orbitals exist? There's 5. So we haven't really listed the quantum numbers associated with all of the 5D orbitals. So the first one would be 5, 2, minus 2. And then there'd be 5, 2, minus 1, and 5, 2, 0, and 5, 2, plus 1, and 5, 2, plus 2. There's 5 of them. 5D. Now, if you just said all the orbitals for n equals 5, there'd be a lot more. I think there'd be 25, actually. So you could think of these as being like a telephone number or an ID number or something for each orbital. Each orbital has its own set of quantum numbers. Now, these are all in the same level. The principal level, n equals 5, they're also in the same sublevel. But then each of them has something that identifies it as being different from the others. Any questions? This is kind of hard in sort of a dumb way because we're not doing any crazy math or anything, right? We're dealing with small integers, but we have to remember what the limits are. Okay, so we talked about atomic spectroscopy, and that's where we got all the pretty lines, different colored lines. Each wavelength in an atomic spectrum corresponds to an electron transition between orbitals. When an atom absorbs energy, perhaps because you're zapping it with electricity, an electron can be excited to a higher energy orbital. So in my hotel, energy is like money. If you want to stay on one of the higher floors, you're going to have to pay more. So generally people come in and they're going to take the lower floors first because it costs less money. But somebody's gambling and they hit a jackpot and they may spring for a room on one of the upper floors. So an electron can be excited to a higher energy orbital. It's unstable up there. It's higher energy. There are lower energy places for it to be. And so eventually, actually it's very quickly, it will relax to a lower energy orbital. When it goes back down, it will release that energy difference as a photon of light. And that is the light that we're seeing coming out of that hydrogen lamp or that mercury lamp. And the energy of the photon corresponds to the difference between the two energy levels, the high one and the low one. So here we have an illustration. Here's n equals 1, n equals 2 is higher in energy, and n equals 3 is higher in energy. So we have an electron that was in the first energy level, the first principal energy level. It absorbed energy. That energy could come from heat or electricity or various different things. But it jumped up to level 3. We say it's excited. Then it's going to relax. It can relax back down to the next lower level, or it could go all the way back down to the level it came from. It can do it in any combination. Just like when you're going down the stairs, you could take them one at a time, or you could take them two at a time, or you could jump from the top all the way to the bottom, depending on your personality, right? And how old you are. So here it is going down to the next level. The energy that it absorbed going up to here has to come out. Energy is conserved. So when it goes down here, now it has lower energy. The energy comes out as a photon of light. And the energy of that photon, which we can measure based on its wavelength, equals the difference in energy between those two levels that it was transitioning between. Now, the electron can't just gain any old amount of energy. It gains an amount of energy equal to a difference between the two states, or the two levels. They're unstable at the high energy, so they'll transition to lower states, and they will emit a photon of light. And that's why we see these discrete lines in the emission spectrum of elements instead of a continuous spectrum, because it's quantized. There are only certain energy differences that the electron can experience. And each of those differences is revealed as light of a particular frequency. We can predict the wavelengths of lines for hydrogen by calculating the difference in energy between any two states. Remember, we looked at that equation for hydrogen, and it was relatively simple. If you have an electron in energy state n, there are n-1 energy states it can transition to, and therefore it can generate n-1 lines. Because if it's in energy state 1, is there anything it can go down to? No, it's already at the bottom. So if n equals 1, then n-1 is 0, you're going to get 0 lines. If there's n equals 2, there's 1 transition. It can go down to number 1. But if you're in energy level 3, it could go down to 2, or it could go down to 1. As it gets higher and higher in n, there's a lot more possibilities for it. And for a one-electron system like hydrogen, both the Bohr model and the quantum mechanical model can predict those lines very accurately. There is, we could figure out the energies of the orbitals with our equations, and it matches up with the wavelengths of light that come out, and it's really, really cool. So this is how they do it. The change in energy is the final energy minus the initial energy. And so we had that equation for the energy of an electron in a hydrogen atom. So here's the final one, minus 2.18 times 10 to the minus 18th joules times 1 over n final squared. And then we subtract the energy of the first one, which is n initial squared. And then you can combine terms and end up with this. The change in energy of the atom is equal to negative change in energy of the photon. And we can calculate the wavelength of the light based on the energy of the photon. hc over E. H again is Planck's constant, c is the speed of light. So for hydrogen, here's n equals 1, n equals 2, 3, 4, 5, etc. So if you were to put the electron all the way up to an infinite n, that would be ionization. You lost the electron. You gave it so much energy, you blasted it out. If it stays in the atom, though, let's say it goes up to level 5, from level 5, it could go down to 2, or it could go down to 3, or they don't show it, it could also go down to 4. There's different transitions possible. These are the ones that fall within the visible wavelength, within the visible spectrum. So going from n equals 5 to n equals 2, we see light with a wavelength of 434 nanometers. The teal line corresponds to a transition from 4 to 2, and the red line is from 3 to 2. These transitions are infrared, that's lower energy. We can't see those. They can be measured, but we can't see them. And these transitions are much higher in energy, and those are in the ultraviolet region of the electromagnetic spectrum. So we don't see those, but they are there. Determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. And I'm sure you don't want to do this, and I don't really feel like doing it either, but we're going to do it anyway. So we're looking for the wavelength of light. And so wavelength of light is related to the energy. We just saw that the wavelength was hc over the energy. So we need to find the energy of that photon or that light. Well, that's going to be equal to the change in energy of the electron, which is the final energy minus the initial energy. Now, you can put all of this together in one big messy equation, but I don't feel like doing that. So we're going to calculate the final energy and the initial energy separately. So the final energy, and we're using, where is it? Energy of hydrogen atom levels. The energy is equal to minus 2.18 times 10 to the minus 18th joules times 1 over n squared. Well, what's the final n in this problem? It's going from n equals 2 to n equals 7, right? So this is n final, so 7 squared. So I'm going to take 1 divided by 7 squared, and then I'm going to multiply that by 2.18 EE18 minus, and that's negative. And so this will be minus 4.44, no, 5.45 times 10 to the minus 20th joules. Okay, I'm using an equation, and I'm plugging in n. It's a kind of an ugly looking equation, but I'm not going to make you memorize it. So the initial energy, we're going to use the same equation, times 10 to the minus 18th joules. I'll write it out this time, like that. The initial energy of the electron is equal to this constant times 1 over the initial n squared. Well, the initial n is 2. So I've got 1 divided by 2 squared, which is 4, times 2.18 EE18. And change the sign. I did something wrong. 1 over 4. So the initial energy is equal to minus 5.45 times 10 to the minus 19th joules. And we're not going to dink around with significant figures on this. It's kind of irrelevant. You still with me? Mostly? So to find the change in energy then, I'm going to take E final minus E initial. So the change in energy is the final minus 4.45 times 10 to the minus 20th joules minus the initial energy, which is minus 5.45 times 10 to the minus 19th F joules. Just be careful with your negative signs there. And I'm coming up with 5.005 times 10 to the minus 19th joules. Yeah? This is the change in energy for the electron. The light is being absorbed. The energy is going into the atom, and that's why this delta E is positive, because it is increasing in energy. The amount of energy that the electron increases has to correspond to the light absorbed. So that's this E that we're looking for over here. I'm going to write this at the top because I ran out of space. So we need Planck's constant, 6.63 times 10 to the minus 34. Joule seconds, divided by, multiplied by speed of light, 8.00 times, no, it's 3, isn't it? 3.00 times 10 to the 8th, that's where the 8 is, meters per second, divided by 5.005 times 10 to the minus 19th joules. So we get joules canceling out, we get seconds canceling out, we get meters as our unit, which is very encouraging. 6.63 EE minus 34 times 3 EE 8 divided by 5.005 EE 19 minus, and we're getting 3.97 times 10 to the minus 7th meters. Is that a reasonable wavelength? What if it was plus 7? Would that be reasonable? No. The amount of, we're talking about light, the wavelength should be small. So we're expecting a negative exponent here for units of meters. So if we multiplied that by 1 to the 9th, I'm sorry, that's not what I wanted to do. 1 times 10 to the 9th, we'd end up with a wavelength of 397 nanometers. So that is equal to 397 nanometers. Any questions?
Where did the C come from again?
C is the speed of light. Yeah, at this point in this sort of a chemistry class, you want to understand as much as you can, but some of it you just kind of have to accept. It's because they said so. Or maybe I kind of followed when she showed how they derived that equation, and I believed it then, so I'll just keep believing it now, even though I can't remember why I believed it at the time. So sometimes you just have to take things a little bit on faith. Any other questions?